Thanks so much, Megan. Yeah, so I don't know if I would consider myself a LANDFIRE super user, but I definitely used some LANDFIRE data in the science that I'll be presenting to you today. This is basically a study we wrapped up and published last year, after which Megan contacted me, and I'm acknowledging a bunch of co-authors. I'm not going to read the whole list here, but this is obviously a very collaborative effort. Okay, here we go. So I'm not going to give kind of a broad overview of prescribed fire because I gather that a lot of people on this call are pretty familiar, but I do want to talk a little bit about prescribed fire and how it might be affected by climate change. So prescribed fire, as we know, is conducted when weather and fuel conditions are considered safe based on ranges of different climate variables, so-called prescription windows. And we're talking here about temperature, relative humidity, precipitation, wind speeds, as well as fuel characteristics such as the fuel type, fuel moisture, and fuel loading. And climate change is already impacting a bunch of these, if not all of them. So we are already seeing increasing temperatures. We're seeing changing precipitation patterns with strong storms in some areas that haven't seen those before, and droughts in other areas. So the hydrologic cycle is intensifying, and we're seeing basically everything amplified. So rain as well as no rain. And then wind speeds are also changing. All of these things impact fuel moisture, and going forward, they will also impact ecosystem composition, what types of vegetation we'll be seeing in different areas. And so future climate change has the potential to even further impact most of those factors that go into prescriptions. And so the question that we asked was, what are the implications for the prescription windows or the periods that are currently considered safe for conducting prescribed fire? And we investigated this question by combining local prescription information with climate and fuels data. And so first of all, I'll give you an overview over the different data sets that we used in our study, and then I'll go over how we calculated our basically amount of burn days per year. And then we'll talk a little bit about the results and what we found. So we are using prescription information from 83 individual sites across the continental US. That's the little map on the lower left that's showing you the locations as stars. And then we overlaid that with statistically downscaled climate data from 18 CMIP5 models for both historical conditions and future projections for 2 different future scenarios. And then we use the LANDFIRE fuels data from the Scott and Burgan Fuel Model as our fuels data, basically. So I'll go over all of those in a little bit more detail. Our prescription data, so again, now I've blown up this map for you a little bit. Can people see my cursor, by the way? Okay,
yes,
awesome.
We're good, we can see it.
So it's overlaid here over the EPA level 2 ecoregions. We did divide this analysis up into different ecoregions because we had limited prescription data. And I should say upfront, we gathered this by reaching out to our contacts and the prescribed fire councils, but we didn't get as much back as we were hoping. So you were maybe looking at this and saying, well, this is pretty sparse in terms of the prescriptions that we actually had. So what we tried to do was to use the LANDFIRE data to allow us to extrapolate to other areas where these prescriptions might also be applicable based on the fuel type that is present. And we limited that to the individual level 2 ecoregions. So the ones that are present in the United States are listed here on the right. So if an ecoregion had a prescription, we then looked at the fuels that the prescription listed and saw if those were present in other areas within the ecoregion. And then we basically applied the prescription there as well. And you'll see in a little bit how that plays out. This is what the prescription data looks like. I don't know how many people have seen this before. It comes in a lot of different formats. I'm just showing a couple examples here, one from Alabama and one from California. So the prescriptions will list these ranges of these different meteorological variables and fuel moisture as well. And some of them have dormant and growing seasons, such as the Alabama prescription. Other ones will only have basically a year-long season, and they will list low fire intensity and high fire intensity, as in both of these, but some of them only list a lower bound and an upper bound. And basically what we did is we gathered all this data into a massive spreadsheet This is just a part of it, where we then looked at, let me just go back a slide. So for example, for the Yosemite, California prescription, the temperature range for low intensity fire would be 20 to 75 degrees Fahrenheit, and for high fire intensity, 76 to 85. So here we would use the lower bound of the low intensity fire and the upper bound of the high intensity fire. And we would say, one might say that it's okay to conduct a prescribed burn within those two ranges. So we would combine them. And then if we only had a low and high fire intensity value, then we would use those as our range. So for this Alabama side, we would say during the dormant season, it's safe to conduct a burn between 35 and 75 Fahrenheit. So there was a little bit of judging how to interpret these because they're not all written the same. But then once we had our spreadsheet, we were able to overlay that over our different data sources. And so we have the locations of the different prescriptions. And then here we have the Scott and Burgan fuel models. They were listed in maybe 90% of the prescriptions we had. The other ones listed Anderson fuel models, which we then translated to the Scott and Burgan so that we would have the same fuels for each prescription location. And then the ranges, which we then converted into scientific units. So minimum and maximum temperature, minimum and maximum relative humidity, and wind speed. The prescriptions also provide bounds on fuel moisture, which we did not use because that is not an output of climate models. So this is basically just a first pass. There's also, wind direction is also listed in the prescriptions, and we are not using that either. And that is because that's a very local thing. And because we wanted to extrapolate the prescription to other areas, the wind direction will basically reflect where's my population center that I want to avoid smoking out, and where's the topography that might channel smoke in one direction or another. And so if you want to apply that to a different location, that doesn't necessarily work. So we dropped that as well. So all the results that I'll be presenting will basically be an overestimate of the potential burn days. It's just a first order, basically, what's the word I'm looking for? Pass at doing this. So this is what the prescription ranges look like when we plot them. So we used the minimum and maximum temperature, minimum and maximum wind speed, and only minimum relative humidity. I'll talk about that more in a minute. And here I've plotted the ranges between the different prescriptions for the level 1 ecoregion. So that's going up one level. There's fewer ecoregions that we're looking at. There's basically 9 that had prescription data. And so this is just to show the variability between the different ecoregions in the prescriptions. So for some, you will see that they have pretty wide ranges, such as the temperatures for ecoregion 6. That's where we happen to have the most prescriptions. So that's why the range here is much wider than for 7, where I think we only had 1 prescription. But there's also variability amongst the ecoregions that is even larger than the prescription variability within ecoregions. So that was kind of an interesting thing to look at. There's one ecoregion that's particularly windy, ecoregion 11. We can maybe look up later if people are interested where exactly that is located. And then for the climate data, we used CMIP5 data from 18 different models. They're all listed here. And we used the MACA downscaled data down to 4-kilometer horizontal resolution. MACA is a statistical downscaling technique, the multivariate adaptive constructed analogs that was developed by John Abasoglu and collaborators. And we used 2 different climate scenarios. So a middle of the road climate scenario, the RCP 4.5. The RCP stands for Representative Concentration Pathways, and the numbers here reflect the radiative forcing that is exerted on the climate. And so this is 4.5 watts per meter squared. And then we have double the forcing almost at 8.5. That is a worst case high emission scenario that leads to a lot more warming than the RCP 4.5. And so this is what the climate looked like, averaging over 10 years from 2006 to 2015 at the top. I'm only showing you results now for RCP 8.5. And this is the minimum temperature on the left. and the maximum temperature on the right. And at the bottom, you're seeing the difference between the historical 2006 to 2015 decade and a mid-century 2051 to 2060 decade. And so we're seeing that both minimum and maximum temperature are basically going up a lot everywhere, above 2 or maybe even 3 degrees Celsius. And it's pretty uniform for minimum temperature. And then there are some areas that are warming more than others for the maximum temperature. And that's in the northern United States, as well as over the Rocky Mountains and into the Southwest. But those differences are pretty minor. I guess the major point is we're seeing warming everywhere. We also looked at wind speed and then the minimum relative humidity. So wind speed is now shown on the left and relative humidity on the right. The winds are highest in the sort of middle part of the country with lower wind speeds over the Rockies and in the western US, as well as in the southeast. And overall, winds are projected by the climate models to decrease over the western United States, as well as in the northeast and the northern United States. But then there are some pockets where they're increasing over here, southern Texas, and then also in this middle part. Relative humidity, we're also only looking at the minimum. As I said, I'll talk about that a little bit more later. Is predicted to decrease everywhere, with the exception of a few areas where the decrease is close to 0, but there's not any increases anywhere. So it's basically getting drier everywhere, for the most part less windy in the western US. And I should say that those are averages from those 18 climate models we're looking at. And there's a lot of uncertainty in those projections. So the individual models might look quite different. And that's why maybe these differences are a little bit more muted than an individual climate model would show. So getting to why we dropped maximum relative humidity from our analysis, that was because the high values basically drove us not finding any burnable days in many of the ecoregions. And a little bit of that has to do with some biases. So Abatsoglu did an analysis of the bias in the GridMet relative humidity, and that is the data set that is used to downscale the climate models. And he found that while the minimum relative humidity had relatively small biases around 0, there was about a 10% bias in maximum relative humidity at a lot of the stations that he compared this gridded observational data to station observations. We did also look at other observational data, including the air satellite observations. And here we also found that values of maximum relative humidity are fairly high, much higher than a lot of the prescription ranges. And we basically decided to drop it because the maximum relative humidity values occur primarily at night when it's coldest out. And that's also when prescribed fires are very rarely conducted, if at all. So these maximum relative humidity values don't really correspond to what is asked for in the prescription, because in the prescription, we're asking if during the day the relative humidity is this high, it might be dangerous to expose people to the heat and the high humidity working outdoors, running the prescribed fire. It's not necessarily that with more humidity, you have more risk of a fire escaping. But basically, they are talking about daytime maximum relative humidity, and that's not something that was available from the climate model data. The overall maximum relative humidity is a nighttime humidity. So it's very high, and we just decided to cut it out of our analysis so that we wouldn't artificially reduce our burn days. So the Scott and Burgan Fuel Model is the other data set that we used. This is just a very brief slide to show you what that looks like. There's a great Forest Service report that I'm sure a lot of you are familiar with that talk about the different fuel models in there. There's basically grasses, shrubs, and timber, and all of those are then further segregated into different types. And there's, I think, 40 different fuel types that we used. And of course, LANDFIRE provides that data set for the continental US. I have here an example for Boulder, Colorado, because that's the last place where I gave this talk, and I wasn't sure where all of you were located. I've now found out that you're all over the place, so I think I'm glad that I stuck with Boulder. It's just as good as any other place, just to show what the fuel data looks like. So I used the LANDFIRE viewer to create these next few slides. And you can see Boulder. I was giving a talk at CU, which is right here. And so I was talking with students about, this is basically how the fuel model sees the region. So we have non-burnable fuels or non-burnable areas with the urban area of Boulder itself. Here's Longmont, another little town. And then we have, lakes, which are also non-burnable. And then east of Boulder, we basically have a lot of grasslands and shrubs. And then here's the Front Range, kind of cutting the slide in half, where to the left we have the Rocky Mountains with a lot more conifer and pine trees. So now I'll talk a little bit about how we did our analysis. It's not really complicated at all, but it's maybe a little convoluted to step through. So we basically took each individual ecoregion, so each of the colored regions in this map, and we asked, does at least one prescription exist for this region? If we have a prescription, then we took the ecoregion and we stepped through each individual 4x4 kilometer grid cell within the ecoregion. And for every day of the year, we looked at, does LANDFIRE fuel basically match any fuel types that are in the prescription? And then if the answer to that was yes, then we overlaid the MACA climate data over the prescription ranges for temperature, relative humidity, and wind speed. And if all of the three of them are within prescription, then we count that day as a burn day. If not, then we don't count it. If it's one or two, we don't count it. All of the three of them have to be within prescription. And so then we basically get a map for each 4x4 grid cell that had the right fuel type. And there was a prescription within the ecoregion, the number of days per year that are classified as burn days. And so that's what that looks like for the historical decade of 2006 to 2015. And this is again for the RCP 8.5 scenario, although the scenarios are basically the same for this historical period. So the map would look the same if I plotted 4.5. And so we had between 0 and 180 burn days a year, with the highest values in the southeast and the northeast, and then much lower values in the western US along the Rockies. There are some pockets of high values in the southwest that I think, there must be something funky going on with the meteorological data, or the fact that we're neglecting all these other factors is leading to these overestimates, because we are definitely not seeing these high amounts of burn opportunities, at least where I live. And I'm sure that Megan can confirm as well. But yeah, so you can see here the regions that are gray were regions where either in this ecoregion, for instance, we did not have any prescriptions, or where we had prescriptions that only covered part of the ecoregion when we overlaid that with the LANDFIRE fuels data. So in this ecoregion, for instance, we have some fuels data that matches the prescription and some fuels data that doesn't, and those areas are then grayed out. And so then we looked at how this available burn day number changes over time. And so here I'm showing you the results for RCP 4.5 at the top and 8.5 at the bottom. And so we subtracted the historical period from a decade in the mid-century, 2051 to 2060. We didn't want to look all the way out to the end of the century, because fuels are definitely going to change, and we are basically only considering static fuels from the LANDFIRE data for the present day. So we didn't want to get too far away from the current climate state, and then it would be hard to make the justification for using the fuels data from 2006 to 2015, basically. But we're seeing that in both of the scenarios, there's a projection for a decrease in burn days in the southeastern US, and overall, more or less an increase in the western US, with some pockets of decreases, both kind of along the west coast and along the southwest, and then also higher up north. Between the two scenarios, there's not really any huge differences. The differences or the decreases and increases are amplified in the 8.5 scenario, where we're seeing more warming. And we're basically seeing differences up to 30-ish days per year. So that's pretty big. That would be like taking a month out of the equation for burning. But again, to reiterate, those 180 days per year that we're seeing as the maximum values are probably overestimates because we're not accounting for those other factors I mentioned. Then we were also interested in asking the question, how do individual climate variables contribute to this change in burn days? So, if we only look at minimum temperature or maximum temperature, how does that drive changes? So you've already seen this slide. Here we're only looking at the differences between the present day and the future in minimum and maximum temperature. On the left here is the minimum, and on the right is the maximum. And then in the next slide, we'll see how that translates to differences in burn days. So on the left now, we're seeing minimum on the top and maximum temperature on the bottom. So if we only had those variables as a constraint and we dropped the wind speed and relative humidity, we would see a lot more burnable days. So now our scale goes up to 360. Basically, the entire year is burnable in some situations. In the minimum temperature scenario, that's more of a constraint in the Western United States and also in the Northeast, a little bit more than maximum temperature right now. And so if we change minimum and maximum temperature, they're both going up, remember? The minimum temperature increase is going to lead to more days that were too cold to burn to come into the prescription band. But the increase in maximum temperature is going to do the opposite. It's going to lead to a lot of days that were burnable before to be too hot to burn. So with the temperature increase, we're seeing an increase in burn days if we just use the minimum temperature and a decrease if we just use maximum temperature. And so you can think of it as a seasonal shift. Basically, in the summer, you'll have fewer opportunities, but you'll have more opportunities in the spring and fall or in the shoulder seasons. And in some locations, also in the winter. And then we looked at the same question basically for wind speed and relative humidity. And so just as a reminder, the wind speed decreases across the Western US. There are some increasing pockets over here and decreases also over the northern and northeastern United States. And then relative humidity decreases everywhere. And so first of all, we're seeing that relative humidity or the minimum relative humidity is not a large constraint at all on burn days. So across large swaths in the US, we have 365 burn days if we just apply minimum relative humidity. And wind actually showed up as our most strong constraint. So it removed most burn days from this map. This is just for the present day. So we're seeing the fewest burn days when we just apply wind speed. We're not seeing huge differences with the decrease in minimum relative humidity. We see small decreases sort of here along the Rockies, and they are a little bit bigger for the higher emission scenario. And then the wind speed, the decreases in wind speed will lead to an increase in burn days. So slower wind speeds generally means it's safer to burn. And the decreases in burn days that we see, the increases in wind speeds, talking about changes and changes and changes, we're seeing increases in wind speed over southern Texas and over here, and those lead to decreases in burn days because stronger winds means that maybe it's not as safe to burn as it was. And so you can kind of already see that these different climate variables play different roles in how they control the amount of days that we can consider burnable. Another factor to consider that I glossed over up until now is inter-modal variability. So we used 18 different models. I'm showing you only 10 of them here, but basically all of them predict different things as well. And I've only looked at the multi-model mean so far. So if we look at the individual models, you can see that most of them, for most locations, so I chose 6 locations within different ecoregions sort of spread out across the United States where we had data. For 5 of them, the models don't agree on the sign of the change. So some of them will be showing increases in burn days, and some of them will be showing decreases, except for the chaparral in California, where every model shows an increase. But that's pretty rare. For most of the other locations, there's a lot of variability. So that's important to keep in mind. And I'll wrap it up with a little summary. So we did show that climate change has the potential to exert a large influence on prescribed fire opportunities, but the picture is pretty complex. So we're seeing both increases and decreases in burn windows, and that's based on the region where we're looking at. Different aspects of climate change drive changes in different regions and in different ways. So, the temperature increase will drive both increases and decreases in burnable days, but it'll probably mostly lead to a shift in the seasonality of burning. And then wind speed might also be a driver of increases in burnable days. However, it's important to mention that wind speed is one of those very uncertain variables in climate projections. And so while we pretty much know that temperature is going to go up and we have high confidence in that, we don't have high confidence in the fact that wind speeds are going to change in a certain direction. So that result, should be taken with a huge grain of salt. I also want to reiterate that our method does overestimate burn days by not considering fuel moisture, the upper bound of relative humidity, as well as local smoke constraints. And we have also not considered changes in fuel composition over time, which we are for sure already seeing shifts in ecosystems. But that was just not possible with using the kind of climate model output that we get. Newer climate models in CMIP6 are now, some of them are projecting vegetation changes, but there's also large uncertainties in that, and those models still have a long way to go before they're reliable. And yeah, that's it from me, and I'm happy for questions and discussion.
Two-parter. One of them is, what's the next step in this analysis? What do you hope to do after this to maybe make the results, a little more useful? Sound like you had a lot of caveats, and that's not surprising given climate modeling. And then the second part is, how do you envision this particular study being used? Is it in discussions about policy or the things? How would we use these results?
So to your first part of your question, unfortunately, this was part of a project that the funding for has ended. And so we currently don't have plans to carry on this analysis. We would need to secure follow-on funding, which we haven't been successful at doing, unfortunately. But, I could see using the new suite of climate models. So CMIP6 and then CMIP7 is going to be coming online in the next couple of years. Those models do predict vegetation changes, which I think would be important to incorporate. We also had some issues getting prescriptions. And so, we did reach out to the prescribed fire councils, but we didn't get the response that we were hoping for. It would be great to get better coverage for an analysis like that. And there have been some other studies that have done it differently. Basically, instead of using the individual prescriptions, they used broader ranges that they obtained by, maybe evaluating prescriptions or talking with managers that are more regionally focused. And so they have more continuous coverage of data across the US. Those are all things that I think would be valuable to do. But like I said, right now, we don't have funding for it. And then in terms of how this data can be used, so this project actually started at Eglin Air Force Base in Florida, where we have some collaborators that we were working with, and they were very interested in the seasonality, kind of knowing, okay, if we're going to be losing days in the summertime, but we could ramp up our burning in October. They had been using October as a kind of transition month before the growing and dormant season, where they hadn't been doing burning before they ramp it up again in November and then through the winter. And so if October becomes a good month for them, then they can shift resources and basically think about how do they basically structure their operations so they take advantage of times when new burning opportunities would present themselves. So we did this analysis for them first, and we had discussions with them where, they were very interested in our results. And I don't know if I would necessarily advocate for people to take these results and use them to plan their operations, but just to be aware that where the trends are going in a particular location. Does that make sense, Jim?
Yes, thank you for that answer, Alex. Pretty much what I thought, but I wanted to get your ideas. So thanks for the presentation and for the question, answering the question.
Were all the prescriptions you gathered for broadcast burning, or did you gather any other types of burning?
You mean like slash pile burning or?
Yeah, jackpot. I don't really know if prescriptions are done for anything other than broadcast, so I just thought I'd check.
I think they were mostly broadcast burning, as I understand it. One of our students went over them and consolidated them. So some might have slipped in that were not, but I think most, because we were asking for that from our partners and colleagues, I think that's mostly what we ended up getting.
And I think that makes sense with your results because you probably would have gotten more burn days if you had included piles, but I just wanted to check. And then another question is, I am really curious about the dead and live fuel moistures, and I can see why, that was difficult to include, but that seems like a really important part of increasing temperatures and decreasing RH, that you're going to have more drought and drier fuels to begin with. And I'm wondering if you have any thoughts on data that might support incorporating those fuel moistures into an analysis like this in the future. Like, what would be needed to do that?
So I think there are some models that take meteorological data that we basically have from the climate models that would translate that to a fuel moisture output. So that could be something that we could use. Yeah, we did not, but I think that there are probably tools out there. Because I think people basically do predict fuel moisture based on meteorological conditions, right? I mean, I guess especially dead fuel moisture, maybe not so much live. That's a little bit more complicated.
Right, right.
So I'm curious about you were talking about how some of the newer climate models are looking at vegetation change through time, obviously interacting with the climate changes. You said there was maybe some problems with it, like it wasn't super detailed or anything. What could you just describe that a little bit more, like what you know about it? Because we do talk about succession a lot in LANDFIRE and trying to capture that those changes through time, especially after disturbances.
Yeah, so I'm not an expert on the vegetation side, but from what I understand, so the generation of vegetation models that was part of CMIP6 is what's called a big leaf model. And so they don't represent the vertical structure of the vegetation that's important for a bunch of different processes. And they kind of just see them as, one big leaf that does photosynthesis and takes water from the soil. So pretty simplified. There are newer generations of vegetation models, such as the FATES model that specifically looks at competition, succession, and those processes in more detail. And again, not being an expert in that kind of stuff, I have a hard time really describing it, but it does take into account more of the vertical structure of the vegetation and other processes that those more simplified models are missing.
Harkening back to 20 years ago, remembering the big leaf aspect. So yeah, that makes sense. And so they're just trying to kind of improve on that. Sounds like,
yeah. I mean, the big leaf models are still being used, I think, in many of the climate.
Do you plan to release the site-specific results for all of the sites with prescriptions to better understand where there is more model agreement?
So we don't have plans to do that right now, but we could. I mean, that would not be a super challenging thing to do, that we could just add to our GitHub where we have our code and data stored. That's a good idea. Thank you.
Is the GitHub repo public?
Yes. Yeah, it's linked in our paper.
Okay, perfect. Great.
Yeah, we have the prescription spreadsheet in there as well as the code that analyzes it. And so if you wanted to run it, you would have to download the climate data and get the LANDFIRE fuel model data, because those are also freely available, and we didn't want to just copy and make data available, in our GitHub that's already available elsewhere.